So we're continuing to be Profinite with Alan Reid from Rice, who's going to talk about profinite rigidity, finite presentation versus finite generation.
Thank you, Kevin. Okay, got it. Thanks. And thanks to the organizers for the kind invitation to come and speak at this conference. Really is a tremendous pleasure to be here. It was a long haul, but it's a great pleasure to be here. And I'd like to thank Radhika and Mahan in particular for organizing some of the transportation to get me from the airport in Mumbai to here. So thank you once again. Okay, so as Karen alluded to, this is kind of a continuation of Martin's talk, and so it'll come as no surprise that this is joint work with Martin and Ryan Spitler, who Martin mentioned before. So what I thought I'd do to begin with is just, even though it was but only 30 minutes ago, I thought I'd give a sort of a Scottish recap of what Martin did. And so unlike Martin's talk, all groups will be finitely generated and residually finite. So residually finite being assumed, it provides this large collection of finite quotients for which one can begin to make sense of trying to understand a finitely generated group by looking at its finite quotients. Buried under the hood at some point there will be groups for which there are no finite quotients, but they won't be quite as explicit as they were in Martin's talk. Okay, so here's kind of a vague version of the theorem that Martin stated. I'll state a more precise version that kind of Martin stated as well, but let's start with this. Let's just say maybe it's an imprecise statement. And the imprecise version is, as Martin was saying, that there are these groups that are profinitely rigid amongst finitely presented groups, but not amongst finitely generated ones. So there exist groups that are profinitely rigid amongst finitely presented groups, but not amongst finitely generated ones. So as Martin mentioned right at the very start of his talk, this was kind of the theme that we'd been thinking about for some time through a process of works that, again, Martin mentioned, and I'll dig into a little bit more deeply, and providing a strategy for which one can execute in certain cases to prove profinitely rigid in various settings. So again, even though it was but a few moments ago, let me just remind ourselves what profinitely rigid means. So we say gamma is profinitely rigid if whenever we have a lambda which is finitely generated and residually finite, whenever there exists lambda with lambda hat isomorphic to gamma hat, then this in fact implies that lambda is isomorphic to gamma. So again, as Martin so eloquently put it, we think of profinitely rigid as basically these little diamonds that we found once they've been taken out of the gutter, clean things up, they are diamonds. That's why we like this kind of picture. And again, even though this kind of hatty guys here looks kind of complicated from the point of view of defining them via this inverse limit of inverse system, in a very basic level, we're asking a very concrete question about to what extent a group is determined by its finite quotients, and that's kind of what we're saying here. Okay. Right. So to state a more precise version of this, let me bring in some other additional terminology. So to state a more precise version, let's bring in some key players. Let's define some key players, one of which, again, you don't get the advantage of having a nice diagram that Martin illustrated. You just have me writing a triangle group. So delta will be the triangle group delta 3, 3, 4. So you have to imagine Martin's picture and not this picture. So here's this triangle in the hyperbolic plane with interior angles pi over 3, pi over 3, and pi over 4. We take the group generated by reflections in the edges of this triangle that defines a discrete group of isometries. It has reflections, but there's an orientation-preserving subgroup of index 2, and that's the one that we will distinguish as the triangle group. And it's presented by, I'll change the notation slightly from Martin's, so C1, C2, C3, where C1 cubed is C2 cubed is C3 to the 4th is 1, and C1, C2, C3 is equal to 1, or this is also presented as AB, A cubed, B cubed, AB to the 4th is equal to 1. So this triangle group is a very beautiful discrete group of isometries, and a feature of this discrete group that, again, will be buried under the hood a little bit in what I describe later is that there's an arithmetic structure to this group as well that's crucially important in what we do. So one of the things that we proved about this group, as Martin said, is that, so theorem, and I'll refer to this as Beamer's, and the M here is McReynolds. That delta is profinitely rigid in the absolute sense. So again, just to be clear, when I say profinitely rigid, unless I say otherwise, I'll always talk about what Martin called profinite rigidity in the absolute sense. So this guy is determined by its finite quotients amongst all finitely generated residually finite groups. So Yair asked about three manifolds, and one of the sort of slight weirdnesses that comes out of what we do is that we would have loved to use the triangle groups to do what we said we were going to do here. Unfortunately, for various reasons that Martin mentioned, and I'll mention again shortly, doesn't quite work. It's buried in the whole constructions of fiber products again. We need to work with certain central extensions of this, so we want to consider, so let's let M be a Seifert fibered space over S, which will be H2 modulo delta, so this is a sphere with 3 cone points, 2 pi over 3, 2 pi over 4, 2 pi over 3. So the quotient is this nice sphere with 3 cone points. A Seifert fiber space is just a closed 3-manifold that's foliated by circles, and when you collapse the circles down to points, typically you see nothing interesting, i.e. the regular fibers just collapse to nice points, and then there's these finitely many exceptional fibers that collapse down to these particular cone points here. And again, maybe Martin mentioned in one of the slides, so this gives a description of the fundamental group of M, which, even though there's infinitely many ways of doing this, as will be visible shortly, I'll just decree all of these be gamma from here on. So it gives a description as there's a center that corresponds to regular fiber delta to 1. So this is going to be generated by Z. And if gamma is then presented by Z, C1, C2, and C3, and this extension's central extension that we get, so Z is central. And then there's various ways that we kind of see the exceptional fibers being showing up. And so what we see then is that we get C1 cubed Z to the E1 equals C2 cubed Z to the E2 equals C3 cubed Z to the E3 is 1, and then C1, C2, C3 is Z to the D. So here, the EIs and the D are integers, and in fact, the way that one normalizes this is that they should be co-primed to 3 here and less than 3, so the EIs belong to 1 and 2 for I is 1 and 2, and E3 belongs to 1 and 3, and D is just an integer. So that's how you get a presentation for the group gamma. Now, the only reason for mentioning this is that, let me just get this here, is that, again, one of the technicalities that Martin alluded to in sort of building these sort of fiber products is that one can check that if you look at H1 of M with Z coefficients, well, it's finite of order 3K, where K is equal to 4E1 plus 4E2 plus 3E3 plus 12D. So this is never 0, and it's always odd, as is kind of readily checked by the normalizations. Now, you may wonder, why would I care about that? Well, you're never going to know today. But it's buried under the hood for doing these fiber product constructions as one of the technicalities for building epimorphisms from groups that allow us to do what we need to do. Okay, so now we can state the more precise version of the theorem. So the precise version says the following. So maybe the first part is that the group gamma itself, just this 3-manifold group, is profinitely rigid. Secondly, if we take 2 copies, this is what Martin was telling us earlier, that this guy is profinitely rigid. Amongst finitely presented groups. But it isn't, and it fails in a rather bad way for finitely generated, that there exist infinitely many distinct lambda, such that lambda is finitely generated, and lambda hat is isomorphic to the profinite completion of gamma cross gamma. Now, you may say, for the first one, let me just make some comments. Well, gamma is profinitely rigid. Yeah, that can't be much of a surprise. It's a central extension of something that's profinitely rigid. Well, again, Martin mentioned this, the world of Seifert fiber spaces that Hempel constructed examples of Seifert fiber spaces that were not homeomorphic, but the fundamental groups were profinitely isomorphic. So just taking central extensions by Z, things can really get quite complicated. And in fact, central extensions more generally, Martin has a student, Pavel Pivek, who proved that in general, taking central extensions of things really does screw up profinite rigidity in a very bad way. So this is a non-trivial statement in itself. But again, to emphasize what Martin was saying earlier, one of the key features is how do you do things? How do you make progress? Well, you try to reduce it to a situation where you think you might make progress. So this part here is that we reduce this to a relative setting. Namely, we'll end up showing that anything that's got the same profinite completion as gamma, it started off in the gutter. But the first step is to show that, that you get this lambda that is equal to pi1 of a Seifert fiber spaces. So not only are you back in the worlds of 3 manifolds, you actually get your guy being a Seifert fiber space again. And then there's work of Gareth Wilkes that says, in fact, that lambda has to be isomorphic to gamma. So Wilkes classified when Seifert fibered spaces could have fundamental groups with the same profinite completion. They fall into this Hempel construction. And the Hempel construction always produced 3 manifolds that fibered over the circle. So they were Seifert fibered spaces. So they're fibered over a 2 orbifold. But in fact, the Hempel examples were always bundles over the circles themselves. In particular, the homology here is finite. So these guys can't fall into the Hempel construction. And so therefore, once we've reduced to this case, that's progress. And then for 3, well, again, what is done here is that we, in fact, moreover, these lambdas, they live inside gamma cross gamma with gamma cross gamma lambda being a Grothendieck pair, i.e., again, just to recall that, well, let me just do it over here. So i.e. Gamma H is a Grothendieck pair if we have the inclusion map U from H into gamma induces U hat, H hat to gamma hat, and iso, so we get failure of profinite rigidity, but U is not. Okay, so again, these Grothendieck pairs are the kind of the seed for constructing the failure. And again, as Martin mentioned, finitely generated is kind of the easy thing that's given. Finitely presented in general is hard. And here they can't be finitely presented for reasons that I'll talk about. Okay, so I think, well, maybe I'm not quite finished yet. So maybe I'll say one other thing that, again, I'd like just to emphasize what Martin said as, again, one of the motivating questions for us, I think, and more broadly, is that, so just remark. So the question, and perhaps even boldly a conjecture now, is that is the free group profinitely rigid? And this is, let's say, n bigger than or equal to 2, as Martin proved. And this is Remesselnikov's Remesselnikov. So the Remesselnikov question. So we don't know the free group is profinitely rigid, and Martin raised the tantalizing prospect is this guy profinitely rigid? Amongst finitely presented groups. And as Martin mentioned, the Platonov-Tavgan construction gives finitely generated groups for which you have failure of this. But there exist finitely generated H with H hat isomorphic Fn cross Fn hat. So again, this kind of set of questions really underpins a lot of what we've been thinking about over the years, and in particular, this version of the theorem that I've written down here that shows this sort of transition between finitely generated and finitely presented. Okay, so I think that ends the Scottish recap. So if there's any questions, I'm happy to take them. Okay, well, thank you. So let's move on. So let's talk about the proof of this guy. And so to do that, I thought I'd say a little bit about the proof as to why delta is profinitely rigid. And this is really part of a framework that, let me just call it broadly and completely immodestly, the Beamer strategy, which sometimes we win, and sometimes we haven't quite won. And the lack of winning is down to various features that I'll touch on shortly. Okay, so let's prove that delta is profinitely rigid. So again, as Martin mentioned, that this sort of seminal paper of Grothendieck back in the day kind of already understood this connection between understanding profinite completion and representations of the group. And here we're going to look at representations in a very restricted sense. We're going to look at representations into PSL2C. I may forget the P, but that would be naughty, but forgive me, I might just write down matrices. So the words that I'm going to write here are Galois rigidity. I'll define this carefully in a little bit. So this is part one of the strategy. And then there's part two of the strategy, which we called somewhat uninformatively the end game. But you'll see why it's called the end game shortly, because in a good situation, you can really push things through and prove profinite rigidity. So there's been a long history of looking at groups that are rigid. So there's the notion of Moster-Prasad rigidity for finite volume hyperbolic 3 manifolds or higher dimensional hyperbolic manifolds. There's super rigidity for kind of higher rank lattices, restricts representations of higher rank lattices. And Galois rigidity is in a similar kind of spirit. It's restricting where complicated representations come from. So this is going to be, so let me put this informally first of all. Let's just say a group G, let's just say sitting inside BSL2C is Galois rigid if it has the fewest possible Zariski dense representations. And for the purposes of today's talk, Zariski dense representation means simply that the image group is non-elementary. So they're a free subgroup. So the full-size representations, what Martin would say. So what might that mean? So let's do delta as an example. And so, as I mentioned, this is presented as a cubed is b cubed is ab to the fourth is 1. So if I'm looking at representations of delta into PSL2C, well, I'm going to send A to some matrix. I'm just going to work in SL2, but there's maybe signs involved. A's got order 3. So where can the image of A go in a representation? Well, it goes in as an element of order 3. That's OK. Or it could be trivial. Well, if it's trivial, that kills this guy. And so kills B as well. So that's not an interesting representation from the point of view of being non-elementary. So we can send A to an element of order 3, and again, Mobius transformation is going to allow us to sort of conjugate things around to look like that, where omega squared plus omega plus 1 is 0, and B will map into something like this. Now, again, it's Zariski dense, so it can't be upper triangular, so this R here should be some non-zero element. And so that's what the representation is going to look like for this triangle group. Now, the condition that we want, and again, similarly, we can't kill B, but what about AB? So AB maps to what? Well, it could certainly map in trivially, again, but if it maps in trivially, that essentially just says the image is cyclic again, so we don't really care about that from the point of view of the assumption. AB could go in as an element of order 2. Well, what could that be? So it could be as an element of order 2. But then what we see then is 3, 3, 2. So that's just the 2, 3, 3 triangle group, which is nothing more than the alternating group on 4 elements. So it's finite. So this is finite. And so again, it's not interesting from the point of view of this hypothesis. And so then AB has to go in as an element of order 4. So that's what a representation looks like on the generators and the product. The relations are satisfied. And what does it mean to have order 4? Well, it means the trace, kind of up to sign, so the trace of, let's call this representation rho of AB is equal to plus or minus the square root of 2. And what is the trace of AB? So that's kind of omega squared plus R plus omega bar squared. So that's equal to plus or minus root 2. And if we rearrange that, we get omega plus omega bar minus 2 plus R equals plus or minus root 2. And so this is that's a square, sorry. So this is just 1, because omega plus omega bar is plus or minus 1. And so we get 1 minus 2 is equal to, so 1 minus 2 plus R, so we get R is equal to 1 plus or minus root 2. So what we've concluded here is that there's only 2 interesting representations from the point of view of what this definition of Galois rigidity is going to be. Fewest possible representation. What would few mean here? Well, notice that the trace field, so if you look at Q adjoin trace gamma, where gamma belongs to delta, well, this is just root 2. I mean, this is 1, and this is root 2. So this is equal to Q adjoin root 2. So minimal number of possible Zariski-dense representations is seen from the trace field. There's just 2. One of these is the faithful discrete representation, and one of these is a representation into SU2. That's all the interesting representations we see. That is the essence of Galois rigidity. Number theory controls all the interesting representations. Maybe I'll go back here. So more generally,
how general is this amongst arithmetic functions?
Well, I'm glad you asked me that. So everybody's favorite triangle group is one that has this. So if we take delta 2, 3, 7, this is Galois rigid. And triangle groups, I've got small character varieties. They're zero-dimensional, okay, because they're just zero-dimensional. I mean, if you just think about doing this in a simple-minded way, you see that it has to be zero-dimensional. one way to think about it is triangle groups don't split, so you can't have curves of characters of representations. So there are always only finitely many points there, but some of them aren't. So let me do this one. So the devil's triangle group, delta 666. This is not Galois rigid. Why? Well, this guy surjects 266. So this surjects delta 6662. And so you get additional characters of representations that show up from this guy that are not, to say the magic words, and hence this word, Galois conjugates of the faithful discrete representation. So amongst triangle groups, and 6 is arithmetic, Galois rigidity happens, but it's not always the case. And certainly that's true. So let me just maybe make a definition here. Let's say G, just some finitely generated group, is Galois rigid if, so how did I write it? And rho from G to PSL2C, a Zariski dense representation, then with trace field K sub rho of G, if the number of characters, so just think traces of Zariski dense representations equals the degree of K rho of G over Q, then G is Galois rigid with field K rho of G. So Galois rigidity kind of says that the only interesting representations come from Galois conjugates of some representation. Typically, we're thinking of subgroups of PSL2C, so they're finite volume hyperbolic three manifolds, or they're kind of Fuchsian groups. So again, Galois rigidity can happen quite commonly for the fundamental groups of hyperbolic three manifolds and orbifolds. So the Weeks manifold is Galois rigid. The group PSL2 of Z adjoin the cube root of unity, that also turns out to be Galois rigid. And so there's a supply of Galois rigid groups that are somehow feeding into the initial statements. So this guy here, delta 334, is Galois rigid. Now, what good is that, you may ask? We'll have to move this now. So what? Well, in certain situations, and in particular for delta, what we land up is the following. So if lambda hat is isomorphic to delta hat, so again, delta here is the 334 triangle group, then what we build out of Galois rigidity is that there exists rho from lambda back into delta. Now, we can all do that, the trivial representation, but in fact, again, it's with large image, with so the number theory of the field, K, let's call it, gives us lots of local representations, so p-adic representations, and because of Galois rigidity, these package together in a unique way and allows us to kind of say that if you have lambda with the same profinite completion, lambda goes back into delta. Now, we would love to do this for delta 237. And, the option for delta 237, the remark, for delta 237, either, and let's just say lambda hat isomorphic to delta 237 hat, either we get, as above, rho from lambda back to delta 237, and then we can execute the plan that I'm about to say, or the bad news is, or we get that there's a representation rho from lambda to PSL2 of the ring of integers of the trace field of Q of delta 237, and this is the ring of integers of Q cos pi over 7. So the point is that, so this group has far fewer quotients than this guy, but the machine only sees things that come from number theory. What does number theory mean? It means congruence quotients. So this guy and this guy have got exactly the same congruence quotients. And so that's why it's hard for us to make progress to say any more than we can say right now. But the hope is that eventually we force it to be inside there, and then what I'm going to say for the end game will it indeed apply there too. Any questions about that? So again, the number theory, yeah. Exactly. But for example, for finite volume hyperbolic three manifolds, it is. It's a consequence of Moster-Prasad. For triangle groups, it is, because there's no deformations. And the way that this thing's been set up, that I got a representation for which I know the trace field's a number field. That's this part. And then the number of characters is that. So it's kind of built into Galois rigidity that whatever this image is, the trace field is a number field. Thanks. Okay, so then the second part of the strategy is the end game. So what we've shown over here is that we've got rho from our fake guy lambda into delta, and let's just say that rho of lambda is equal to L. This is some non-elementary subgroup. So something that we showed in another paper is that if L is a proper subgroup of delta, so it's non-elementary and a proper subgroup of delta, then L has a finite quotient that delta does not. So L has a finite quotient Now that's good. Why? Well, if L has a finite quotient that delta does not, well, that means that lambda has a finite quotient that delta does not, but lambda and delta were meant to have the same finite quotients, so that's illegal. And so the only way we can get out of that is if lambda surjects onto delta. But this implies, since lambda hat is isomorphic to delta hat, that lambda surjects onto delta. So we now have lambda surjecting delta. Now we put hats on this, but this is then isomorphic to delta hat. And so we have an epimorphism now from delta hat to delta hat. Profinite groups, finitely generated profinite groups, have the Hopfian property, i.e. this epimorphism is also an injection, so there's an isomorphism here. So all of these maps are iso, and so what we get is then lambda is isomorphic to delta. Okay, so that's the Beamer strategy, and that's what we do to prove the classes of, and again, buried in this part here of the representation, uses the arithmetic structure. And so that's why we're limited to a finite number of examples right now, which, you know, we think is pretty cool. Now, you may ask, what does finite mean? Is it a billion or is it 7? Well, it's closer to 7 than a billion, but we'd like to sort of shift the needle a bit, and that's proven problematical. But now we do know that we have these kind of interesting classes of three manifolds that we get from the Zypher fibers that will be profinitely rigid. Okay, so how do we prove that gamma is profinitely rigid? Well, we'd like to execute the same plan. Okay, so to prove gamma is profinitely rigid. So again, remember gamma is this central Z extension of delta. we want to follow the same plan. So we want to prove kind of this definition that we've got Galois rigidity for this Seifert fiber space group. But let's think about that. That doesn't seem so surprising. If you take a non-elementary representation of the Seifert fiber space group into PSL2C, well, this center has to die because it's a non-elementary image. So anything that you see as a non-elementary representation comes from delta. So the only interesting representations, again, come from delta. So the only representations are the two that we see here. So this follows. So the Galois rigidity follows since the center dies in any non-elementary representation. And then there's some version of the endgame that I'm not going to get into, but again, one gets a homomorphism from the Seifert fibers, from the fake guy, into delta with large image, and you can essentially run what I just said to prove, so you can sort of follow the above to get that lambda is actually isomorphic to a Seifert fiber space over this guy, S, and then Wilks kicks in. So that's this reduction here. Okay, so it's the same strategy with a little bit more complication. That's the takeaway from this. But the key framework is this kind of strategy. And I should say that the Galois rigidity machine that spits out representations, I mean, that was kind of well known in some sense. And the reason that Martin and myself and Ben and Ryan could make progress is that we kind of understood low-dimensional orbifold groups, as Martin was saying earlier. You can run a similar thing, and if you wanted to prove that SL3Z was profinitely rigid, well, in fact, this kind of machine reduces you to the case where you may as well just consider subgroups of SL3Z. So that's still open, but that's one of the challenge questions to think about. Okay. Maybe I forgot to say one thing, but I'll maybe just make it as a remark, just because, you start to realize when you deal with profinite things, as Martin said, that torsion can show up just for bizarre reasons, and other sort of weirdnesses can happen. And another kind of remark that it doesn't really affect anything that goes on here because we're so lucky with the fact that we're dealing with these central extensions of Fuchsian groups, is that the center can just get bigger in the profinite completion. And that's one of the reasons that, one might worry. So for example, if you take SL3Z, the center of SL3Z is 1. But in fact, the center of SL3Z hat is not 1. In fact, it contains a countable direct product of cyclic groups of order 3. So the center just, boom, just gets gigantic. And, it's the kind of thing that freaks you out. Luckily, we didn't have to deal with that, but it does give one sort of cause for caution. Pause for caution, rather. Okay, right, let's buckle up and think about direct products. As I think you would take away from Martin's talk, direct products, I always like how Martin talked about it. When we were kind of small children, he would kind of introduce kind of direct products. He would start with something like with Z, and he would say, if you're a free thinker, you take the free group, but if you're not a free thinker, you take the direct product. And somehow taking the direct product just makes your life much more complicated in ways that I don't think I really understood until I started hanging out with Martin and seeing kind of the Platonov-Tavgan results. They're just incredibly complicated groups. Okay, so direct products. Okay, so we've kind of sketched the proof, or the ideas in the proof that the Zipher fiber space guy is profinitely rigid. And then we get to the direct product part. So what are we going to do? Okay, so again, Martin said some of this, but the idea is the following. Suppose we've got lambda with lambda hat isomorphic to gamma cross gamma hat. And again, gamma is one of these Zipher fiber groups. Then one, we kind of arrange that, in fact, we're in the setting of a Grothendieck pair. Secondly, show that lambda is not finally presented. And this is sort of building on the ideas in Brights and Wilton, and going back to Baumslag and Roseblade that Martin mentioned. And then thirdly, constructing such lambda. Okay, so that is the strategy that we want to kind of execute here. And the first thing to say is, well, in the previous strategies, we use Galois rigidity. Now, if you look at the direct product here, you know, whatever Galois rigidity might mean, it's clear we're kind of in trouble because we've got two copies of gamma here. So we've got representations that go into SL2C from this guy, and we've got representations that come in from this guy. But again, when looking at non-elementary representations of this guy into PSL2C, I mean, they don't have big centralizers. And so again, what we'll end up kind of seeing is that, well, then there is a sort of shadow of Galois rigidity, i.e. the only Zariski dense representations are the ones that we've seen before that come through factoring the two factors. So even though we do not have Galois rigidity, there is enough for us to start the strategy. I.e., the only representations are the one that come from each factor. The only Zariski dense reps are the ones from each factor.
For this step, could you have arbitrarily many, or is that a subgroup?
No, this can be arbitrarily many. It's just for our, well, Martin's an adult, he can deal with arbitrarily many factors, but you know, for my small-mindedness, I can only deal with two factors. Okay, so let me first talk about part 3 here. And this is where Martin was discussing the basic Platonov-Tavgan strategy for constructing finitely generated groups using the fiber product to give examples of the same profinite completion. And as he mentioned, it gets somewhat more technical here, and he described it as the ugly but useful kind of version. So let me write it down again in a slightly paraphrased version. So what we need is the following. So for 3, we use the following theorem. Now, as Martin said, this can be confusing, and it certainly confuses the heck out of us, and I may even write this down incorrectly. But anyway, I can guarantee you this is true. We wrote it down carefully. But anyway, I did my best to try and not confuse with notation either. So there'll be deltas and gammas with 1s and superscript to indicate they may not be what you think they are. Okay, so let's let delta 1 be a non-elementary hyperbolic group. Gamma 1, a group with H2 gamma 1 Z is 0, that maps onto delta 1. Let's let G be a finitely generated group such that G maps onto the commutator subgroup of gamma 1. Then there exists an infinite sequence of subgroups Pn and G cross G such that Pn, so we get a Grothendieck pair. Okay, well, that's impossible to really understand without me kind of saying what you should be thinking about here. So gamma 1 is not gamma, but the commutator subgroup of gamma 1, this is gamma. And delta 1, this contains delta of index 2. So this gamma 1 is the Seifert-Fibered space orbifold group whose commutator subgroup is equal to gamma. And we have the property that H2 is 0 because everything we're doing is 3 orbifolds. But we do use, when it comes down to it, we do use the fact that H1 of this Seifert-Fibered space is odd order. Now, that just seems kind of completely crazy, but it's in there under the hood, lurking as some technical jiggery-pokery that we can't get away from right now to build this kind of construction to give us examples that we want. Okay, so that's part 3, the ugly version, or whatever you wish to call it. Okay, yeah, Katie.
Is manufacturing something whose commutator and subgroup is this fixed group, is that hard, or is that standard?
It's not a standard trick. I mean, I think it took us longer than we would care to admit in public. We've just admitted it, and that's something that.
Yeah, that seems like a weird thing.
Yeah, and it works in this example. It doesn't work in all the examples that we have, and that's one of the reasons we can't write down all the triangle groups that are profinitely rigid have this property that 334 has. I could replace 334 with 336 and 255 because their Seifert-Fibered spaces that we look at are always got finite cyclic first homology that allows us to run this kind of crazy argument to build these Grothendieck pairs.
So what's the trick here? You're using finite cyclic odd.
Yeah, exactly, right. And that gets buried into some little homological calculation to allow us to deduce what we say here. No, it's almost worth not putting this down because, it's like, what the heck is this? I mean, really. But it's kind of a key part because there's this beautiful framework that goes back to Platonov, Tavgan, and really developed by, Bridson, Grunewald, and then, Bridson individually that gives this machine for constructing Grothendieck pairs. It just never quite works for what we needed, and so therefore there was a good deal of effort expended to get this kind of statement. I mean, all our worries would go away in some sense. I think I got this right. Warren can correct me. If we could prove there was an integral homology 3-sphere that was profinitely rigid, then I think we'll be in business, because then H2 is 0, and we don't have to worry about anything, and there's all sorts of lifting to central extensions of various groups, and so, yeah. Okay, let me comment briefly on 2. So this is this no finally presented thing. So the setup we have here is that we've got 1 to z cross z to gamma cross gamma to delta cross delta to 1. And then we're assuming that we now have lambda that lives inside there as a Grothendieck pair. And we want to show that it's not finally presented. So remember what the the Baumslag, Roseblade, Bridson, Wilton kind of stuff said here is that finite presented subgroups were closed in the profinite topology, so you couldn't have finitely presented guys giving you Grothendieck pairs. So we call this guy P, and we look at P of lambda here. Well, so this guy's still finitely presented down here, and in fact it's because lambda hat is the same as gamma cross gamma hat, it projects to a kind of a dense subgroup of the profinite completion here. So in fact, the Bridson-Wilton idea tells you that P of lambda has to be kind of delta cross delta. And so what we need to do is understand how lambda meets the central Z cross Z. And in fact, what one can show using the so-called magic word goodness of the profinite completion is that, in fact, the center has to be contained inside lambda. This is by this notion of goodness that's due to Serre, that's a cohomological condition on the profinite completion with continuous coefficients, with continuous cohomology with finite module coefficients, and the discrete cohomology of the discrete group with the same module coefficients. So these central extensions and direct products of such things are good, and so we can use that. So again, that's kind of a standard thing. And then the real excitement is actually kind of proving this part here. So the real work. Well, I say real work. I mean, this is real work here, but it's of a different kind of flavor, is in 1. And so here is where we kind of exploit the shadow of Galois rigidity that we see for gamma cross gamma. And what we can show is that there's enough Galois rigidity to get a homomorphism lambda to delta cross delta. Again, it's the same kind of strategy we tried to execute before. We get these representations. And what's the point about this? Well, with image, a full subdirect product. So the subdirect product means whatever the image is, it surjects onto each of these two deltas, and the full part means that it meets each of these factors non-trivially. So it's some complicated image group in here. Now, moreover, the machine that we use actually constructs a factoring that looks like this, where lambda 1 is the image of lambda. So we are viewing now, we've got lambda hat isomorphic to gamma cross gamma hat. We've got lambda living inside there. So we identify lambda with its image in the hatted version of gamma cross gamma. Then lambda 1 is the image of lambda in gamma hat cross 1, and lambda 2 is the image of lambda in 1 cross gamma hat. And then miraculously, so let me just put squiggly arrows here, one can show that these lambda i's are the fundamental groups of Seifert fibered spaces. Moreover, they're actually isomorphic to gamma, using works of Wilks again. So lambda 1 is isomorphic to lambda 2 is isomorphic to gamma. Then using the fact that we have this diagram that lambda is isomorphic, the hatted version is isomorphic to gamma cross gamma hat, and this diagram in the Hopfian property, then this implies with some work that lambda lives inside gamma cross gamma. Okay, I think I'll stop there. Thanks.
Okay, thanks, Alan. Any questions? Any more questions, I should say, for Alan?
This last thing I missed is this lambda 1 is the image of lambda in
Gamma hat cross 1.
Sorry. Thank you. How do you construct this? Just by projecting?
Projecting, right?
Okay.
Exactly.
So I have a question. I think I missed something. You said PSL2 Z omega is Galois rigid.
Yes.
What about the other Bianchi groups?
Excellent question, and the answer is no.
Oh,
And the reason for no is that you kind of like this, I think, because it takes you back to your childhood. You see, if you look at PSL2 of Z adjoint I, so let's think about the cusps of these Bianchi guys, right? So the cusp of so we've got H3 modulo PSL2 of Z adjoint omega. It's this one cusped guy. But what's the cusp cross section? It's a Euclidean orbifold, the 3-3-3 spherical orbifold, because omega, the cube root of unity, you can get omega 0, 0, omega bar as an element of the Bianchi group. And so the cusp is this triangle orbifold. And so that's rigid. So there's no deformation theory a la Thurston's Dane surgery theorem. But for O1, you get that I00 minus i's in the Bianchi group. And so the cusp end is a sphere with 4 cone points of cone angle pi. They do deform.
mm-hmm.
And everything else is just torus cusps. So the Thurston-Dane surgery theorem gives you lots of representations there. The punchline is that this is the only guy for which the character variety is 0-dimensional. And in fact, it's stronger than 0. It's 2 in the sense of just looking at irreducible characters. So that's why we can't do other Bianchi groups. That's why we can't do the figure 8 note. So Galois rigidity, and that's why we can't do the free group. There's just too many characters around. So the fewer the characters, kind of the better.
I see. Oh, thank you. Any other questions? So if not, let's thank Alan again.